Can you, yeah.
This is the last day of our conference.
You have to use the microphone, yeah.
Once more, good morning. This is the last day of this excellent conference in Brazil. Fortunately, in some sense. Today, I'm very happy to introduce you, our plenary speaker, Daniele Bartoli. He's a very active researcher, and I learned a lot from a widespread interest of research interests in his papers. And today, he is from University of Perugia, and his talk today is titled "Recent Results on Scattered Spaces and MRD."
Okay, yes, that's okay. Thanks a lot, thanks a lot. So first, can you hear me? Yes, I guess, yeah, perfect. So first, I would like to thank the organizers, the organizing committee, for this invitation. I really appreciated it. For me, it's always a wonderful experience to be here in Brazil, and especially in San Carlos. I always feel surrounded by not only good mathematicians, extremely good mathematicians, but also good friends. So thank you. And also, I would like to thank all of you for being here. This is the last day of the conference. Yesterday, we had the social dinner, so I really appreciate you being here. So let's talk about mathematics. As you can see from the title of my talk, I would like to present you results concerning a specific type of codes, so-called rank distance codes. But I would like also to talk about connections of these objects with other objects, interesting objects, in particular linear sets or scattered linear sets in projective spaces over finite fields. But also I would like to talk about possible ways in order to construct these objects, and then the tools that you can use, and in particular algebraic varieties over finite fields. We will see in a few seconds. So first, let me start from what could be an interesting question. So suppose that you have your vector space, say that it has a certain dimension n over a field. Now, you can always see the endomorphism, the k-linear endomorphisms of V. You can always consider them. Well, a question could be, how large can what could be a large subset of endomorphisms which are invertible? Well, perhaps this question is a little bit stupid in the sense that clearly you can just take the set of automorphisms of V. No? They are invertible by definition. Well, let's just rephrase this question. So what if now I request that my subset of endomorphisms is also closed under addition and multiplications by elements of K? And now I require that apart from the zero endomorphism, which is always there, all the elements I'm selecting, they are invertible. Then this is not a trivial question now, but as always in mathematics, let's try to generalize it. So what if now I require that my subspace of endomorphisms, it's made not just by invertible elements, but also elements having a certain rank at least. So bounded by below, say n minus 1 or at least n minus 2 and so on. This could be even more interesting as a question. And so let's try to even generalize it. So what if now I have two vector spaces, clearly all over the same field K, and now I consider the set of homomorphisms between V and W. And then I still require that I want to have a subspace of homomorphisms, and each element apart from the zero homomorphism is of a certain rank at least. Okay? So if you're interested in these questions, then just stay here because I would like to talk about these questions and the possible answers, specifically for some instances of some parameters I will talk about. So, as always, you can assume that V and W are K spaces, so they are isomorphic to K to some power, finite subspaces. And in particular, the set of homomorphisms can be seen as a set of matrices M by R. Okay? Now, the conference is on finite fields, so from now on, we can suppose that both V and W are Fq subspaces. Now, I will give you the main definition of this talk. I would use the term code in a slightly different way with respect to what Ferru did, because here now the code words are matrices, yeah? And clearly I will consider a different metric, so a different minimum weight, a different minimum distance, and in general, a different distance between code words, as we will see in a moment. So what I call a rank metric code now is the following. I want to find an Fq subspace of matrices of a certain dimension, so say M by R, and here I would like to consider the following minimum distance, so which is basically just the minimum of the ranks among all the elements, which I call now code words in C, apart from the 0, 1. Okay? This makes sense. It's a good choice of a rank. It's a good choice of distance between elements or weights over elements. Well, these objects have been investigated in the last years, but the first definition dates back to the work of Delsart. And in particular, in his seminal work, it was in his PhD thesis, he also investigated bounds on the parameters. What are the parameters of these codes? So clearly you have the dimension of the matrices here, you have the dimension of this Fq subspace, and also you have this very important parameter, which is the minimum distance. And so you can expect that they are linked by some inequalities. And one of the most famous one, perhaps the first one, the first one who was investigated was this one, which was named the singleton-like bound, just because it recalls the singleton bound in a normal setting. And as we do for MDS codes, we say that a code, an RD code, is extremal or maximum if this code attains here with equality, this inequality here. So they are extremal objects, and somehow they could be of some interest, yeah? But then what I did now is to give you a definition of a mathematical object. So as always, you can ask yourself, okay, this guy just gave me this definition, but then is it interesting really? We are mathematicians somehow, no? So we can always say, yeah, it's very interesting because it's a mathematical definition. But somehow it could be more interesting if you can give connections of your object with other areas of mathematics or applications, unfortunately, yeah? So fortunately, these guys have been found to be interesting also for applications. I wouldn't go into the details, but they can be used in the so-called network coding. And also you can require extraordinary properties for your codes. So for instance, minimality or intersection properties somehow. So you can really try to find applications for these codes. So they are interesting. Trust me. So, but also they have been found to have connections with more theoretical areas of mathematics. And in particular, in this talk, I would like to give you some insight on the connection with linear sets, but also many other connections like semi-fields and so on. So they are really important from many points of view. Okay, so I think I convinced you that they are important somehow. So next question. How many of them there are? I mean, yeah, whenever you have an interesting object, it could be that it's so easy to get these objects, so you are not interested anymore. Or they can be too difficult to be found, so you just give up. So if you're interested in this type of questions, so how rare they are, basically, I would like to advise you to check the answers to this type of questions in this very interesting paper by who recently appeared by Gruizza, Ravagnani, Schicchi, and Zullo, in which they basically prove that for many instances of the parameters, these codes are somehow rare. But okay, it depends on what's the meaning for you of rare. But I would say that, yeah, they are rare, but not so rare. So we have hope to find them, to construct them, to classify them, and so on. Now, okay, it's something worth investigating. So the other question, I mean, the first interesting question is how to construct them. Well, if you're interested in this question, for some instances of the parameters, I would like to give you constructions or ideas of constructions. But also you can ask yourself, okay, I have my RD code. What are the things that I have to check in order to say that my RD code is an MRD code? And again, I would like to give you some ideas. So stay here if you want to know something in this direction. Well, okay. Let's go on. So, first, in all the remaining part of this talk, mostly, I would be interested in specific instances of the parameters. I told you that an RD code is a subset of matrices, a subspace of matrices, so clearly you can change dimensions. But now, let's focus on the case in which M divides R. No? So, in other words, we can assume that the W here is of dimension m over fq, and v is of dimension m times s over fq. Now, this is the general setting, but since you can have that an fq space of dimension m can be seen as the field fq to the m, we will use this assumption here. And also, we will use the fact that in this case, we can consider v to be fq to the m to the power s. Okay? So we will consider fields instead of simply vector spaces. Well, so in this context, again, let me repeat, M divides R. So it's a specific instances of the parameters. Then I would like to describe these objects via so-called linearized polynomials. So they are polynomials whose monomials are just one variable to the power q to the I. Q was the size of the ground field, and the coefficients, they vary in the field fq to the m, okay? Now, why can we use this set of polynomials? Well, because if you just take the quotient with respect to x to the power q to the m minus x, then this guy becomes a ring with respect to composition. You can sum them, you can multiply by elements in fq to the m. So it has a very nice structure, and it is also isomorphic to the set of endomorphisms of the field fq to the m over fq. Yeah? So these polynomials, they really describe the set of endomorphisms in this case, yeah? You can even generalize this idea, so not just linearized polynomials in one variable, but you can use many variables, x1, xs, and you are considering now multi-linearized polynomials, that is, polynomials having monomials which are q powers of just one of the variables. And the coefficients are still in fq to the m. And again, the use of these polynomials is very good in the sense that they can describe in a very good way, because it's an isomorphism, the set of homomorphisms between V and W, in this case. So it could be really the right context. Well, so this translation between matrices and linearized polynomials is so good in the sense that we can really describe the rank, so the concept of weight that we introduced before, via the same concept here in among linearized polynomials. So let me be more precise. If you have, for instance, two matrices here, you can describe the uniquely associated element here, and the set of multilinearized polynomials, and the rank of the difference of these two matrices is precisely the rank of the difference of the two multilinearized polynomials. So you can really describe your code either via some matrices, some Fq subspace of matrices, or some Fq subspace of multilinearized polynomials. Okay, and so the idea is, okay, we have in this case this possibility, why don't we use it? Okay, so for instance, let's stay with the case, with the most easy case. So M divides R, but why don't we consider M equal to R? So that is the case in which the matrices are squared matrices. Well, in this case, if you also consider the minimum distance to be equal to M, then you are searching for, if you are interested in MRD codes, you are searching for codes having Fq dimension precisely M. And in this case, again, in this very nice paper, the authors could show that in this case, the MRD codes are called the full rank, it's obvious, and they are in correspondence with the finite semifields of dimension n over the field Fq. So again, you have your guys here, which are basically equivalent to a very nice structure, algebraic structure. Now, what if you want to consider MRD codes having minimum distance not equal to the maximum possible, but just something less? Well, the next easy case, the most important case, apart from D being equal to M, is the fact that the case in which D is equal to M minus 1. Yeah, in this case, if you just plug in the parameters in the singleton-like bound, you end up that the Fq dimension of C must be equal to 2M. So, since we are interested in subspaces of matrices or subspaces of linearized polynomials, if we want to construct an MRD code in this case, we must provide a basis of it of dimension of size 2M, which could be a lot. So the idea is, okay, why don't we consider something stronger? So here we require that our code C is not just an Fq space, but it is an Fq to the M space. So it is linear over a larger field. Why could be an advantage? Well, because in this case, an MRD code, which is also Fq to the M linear, has dimension over Fq to the M just equal to 2. So it could be much more easy to consider these type of codes because you have to select a basis of just 2 elements. Well, but then since we started from something general and we went into a more specific case, we could be afraid that this specific setting is basically empty. But it's not true, because one of the most easy example of MRD code is known to be the Gabidulin code. And for these choices of the parameters, there is a very, very nice description, very easy description in terms of linearized polynomials, because in this case, you can just consider all the linear over Fq to the M combinations of the polynomials x and x to the power q. And in this case, any linear combination of these two linearized polynomials gives rise to a linearized polynomial who has rank precisely, or at least, m minus 1, because the kernel is at most of size 1 over Fq. So really, this example gives you an MRD code, at least with these parameters. So the hope is that there are many more examples, just requiring something additional, that is that your code is also linear over a bigger field. Well, so in general, what you can do is, again, for these parameters, to search for pairs of linearized polynomials in a way that any linear combination, Fq to the M linear combination of them, gives rise to a linearized polynomial whose kernel has dimension at most 1 over Fq. So how can I select these two polynomials? Well, I don't know if this condition tells you something, but the first time that I saw this condition, then it recalled me another condition from a different perspective. So different concept attached to different objects. But this is how mathematics work. Huh? So, and the concept or the object I was referring at, it is given by so-called linear sets of projective spaces. So let me just give you a short introduction on this topic. So now I have a field, Fq to the m, as in the previous case, and I have a vector space, Fq to the m to the power r plus 1. Now, inside this vector space, I can choose a subspace, an Fq subspace, say of a certain dimension n. Now, if I consider all the non-zero vectors in capital U, I can see them, they are r plus 1 tuples, so I can see them as the coordinates of a projective point in this space here. Huh? So dimension r over Fq to the m. Now, if I collect all these points, whose coordinates are non-zero vectors in capital U, I end up with a so-called Fq linear set of this projective space. And I also say that its rank is precisely n, the Fq dimension of the underlying vector space U. Now, it's very easy to check, to have an upper bound on the number of distinct points here. Why? Well, because whenever you have a non-zero vector here, you also have its non-zero scalar multiples. And they give rise to the same projective point, clearly. So each point is taken at least q minus 1 times, and this is precisely the number of non-zero vectors in capital U. So an upper bound for the number of projective points in this linear set attached to this guy of dimension n is given by q to the n minus 1 over q minus 1. In case of equality, you say that L of U is a scattered linear set, or capital U is a scattered subspace. Now, for scattered subspaces or scattered linear sets, you also have a bound on the rank. And Blockhaus and Lavreau proved that n is upper bounded by this quantity here, which depends on the extension of the field or the dimension of the projective space. Okay? And in case of equality here, you call the Fq scattered subspace or the scattered linear set a maximum scattered linear set or a maximum scattered subspace. Okay? So, connections of these objects. Well, these objects have been investigated first because of their connection to constructions of so-called blocking sets. They are a very special type of subset of points in projective spaces, projective planes, actually over finite fields. But later on, they've been found to be very interesting because of their connections with other objects in projective spaces, translation caps, translation hyperovals, two intersection sets. And clearly, all these objects, they also have a nice connection with coding theory because they are in one-to-one correspondence with many interesting codes. But also, they are connected again to finite semifields, so algebraic structures over finite fields are in general very interesting connections. So linear sets and scattered linear sets are somehow important. Well, before giving you the connection between MAD codes and scattered guys, I have to slightly generalize the notion of scattered linear sets. So here it was our ambient space. So let us consider now an Fq to the m subspace. We can intersect this W with the Fq subspace capital U, and clearly we end up with an Fq subspace. And we can say that it has a certain dimension. Now, with this in mind, the definition of H scattered subspaces is the following. So you have your Fq subspace, and you just require that for any Fq to the m dimensional subspace in this big space, its intersection with capital U has bounded degree, has bounded dimension. And this bound is the same as the dimension H of W as Fq to the M subspace. So if this happens, you say that this guy U is an H scattered subspace, or the corresponding L of U is an H scattered linear set. Okay. Wow. First of all, one scattered subspaces following this definition, they are precisely scattered subspaces following the previous definition. And Chaibok, Marino, Polverino, and Zullo could prove that if you have an H scattered subspace, either it corresponds to a so-called subgeometry, or its rank is bounded by this formula, which is precisely what you expect to be the generalization of the previous formula to the case H larger than 1. And in case of equality here, you say that your subspace, your H scattered subspace, is a maximum H scattered subspace. Well, okay, I just, in the last 5 minutes, I told you many things about these objects, but the main topic of this talk was MRD codes. So what is the connection? Well, first, whenever you have a linear, an Fq to the M linear RD code, you can describe it via an Fq to the M basis. No? Say that it has G1, Gk as a basis. Now you can consider it, and this is done by linearized polynomials, multilinearized in general. So you can consider the following subspace in this vector space here, just considering the multilinearized polynomials, which are the basis of G, and evaluating them into, over the variables which vary in the whole field Fq to the M, okay? So the corresponding set of vectors is clearly an Fq subspace just because you are using linearized polynomials. So this guy, UG, is an Fq subspace which can be used to produce a linear set. And following this theorem by Zini and Zullo, in the case in which some conditions are satisfied, so in particular H plus 1 divides K, so a linear set of a certain rank in this projective space is maximum H scattered if and only if the corresponding code, this is an if and only if, is an MRD of a certain dimension, but it is Fq to the M linear. So, in other words, the objects I defined so far, the so-called maximum H scattered linear sets, for some instances of the parameters, they really correspond to MRD codes, which are of a special type, Fq to the M linear. So these are the geometrical counterparts, in these cases, of MRD codes. Okay, so now we have this correspondence. You can ask yourself, okay, what should I do with this correspondence? Well, if you are interested in a scattered and maximum scattered linear sets, I would say that these objects are not so rare in general. So you have hope to construct MRD codes via this correspondence. On the other hand, sometimes in order to obtain examples, you impose some prescribed shape to the linear set, to the scattered linear sets you are considering. And mostly there are two ways in my mind in order to get these objects, these geometrical objects. The first one is more synthetic. In other words, it's more geometric in the sense that you use projections or you use intersections in order to get this Fq subspace. On the other hand, you can try to directly construct examples via some parametrization. And these parametrizations, they are given by linearized polynomials, as we will see in a few slides. And let me also tell you that I like more this approach, not just because it's more direct, but also because in this way I can use some tools from algebraic geometry over finite fields in order to get characterization results, non-existence results, or constructions. So let's see an example. So suppose that I would like to consider MRD code in which M is precisely, so squared matrices, they correspond to squared matrices, and I would like to get something which has dimension 2 over Fq to the M. In other words, I'm interested in scattered linear sets which are maximum scattered in the projective line. And in this case, by definition, I need an Fq subspace U, which has dimension M. And apart from just changing a little bit the shape of U, I can always consider without loss of generality that capital U has this form. So X varies in the whole field Fq to the M, and F is a linearized polynomial. So when I say the parametrization, I meant exactly this form. So my idea is, okay, what can I say about this F giving rise to a scattered linear set or a scattered subspace? Well, in this case, we can just use the notion of scattered polynomial given by John Shickey some years ago, not that many. So you say that a certain linearized polynomial is scattered if this capital U, this Fq subspace, is maximum scattered in the projective line, okay? So the idea is, how can I get scattered polynomials? We already know one of them. It's x to the power q, because it generates the Gabidulin code. But what about other examples? Well, and here it comes the connection with algebraic curves that I mentioned before. If you're interested in polynomials, which could give rise to maximum scatter linear sets, then you can investigate this curve, okay? This is just the affine equation of a curve, which is embedded in a projective plane over Fq to the M. This is really a curve in the sense that the denominator divides the numerator, okay? And the geometrical equivalence between maximum scatter linear sets and curves of this type is the following. So your guy is a maximum scatter linear set, or in other words, F is a scattered polynomial, if and only if this curve possesses Fq to the M rational points only of a certain type. So just x comma y, where the ratio is an element of Fq, apart from infinity. Infinity, it means that x is 0, okay? So the only Fq to the M rational points of this curve must be of a certain type if you want that F is a scattered polynomial. This is a very strong condition. And how can I use this geometrical characterization? Well, in the following way. Suppose that the degree of this curve is small enough, usually smaller than the fourth root of q to the m. In this case, I'm in the Hasse-Weil scenario, and I can use Hasse-Weil theorem in the following way. Suppose that I can prove that this curve either is absolutely reducible or it contains absolutely reducible components defined over the ground field of q to the m. Then I apply Hasse-Weil theorem to that component, and I end up with the fact that this curve possesses many Fq to the m rational points, and not all of them can be of this type. So this is a way in order to say that a certain polynomial f is not scattered. So this can help you in finding characterization results or non-existence results. And the problem is, how can I investigate such a curve? How can I prove that this curve possesses suitable Fq to the m rational components which are absolutely reducible? Well, I can use techniques from algebraic geometry. I can investigate branches over singular points. I can try to directly factorize this polynomial. I don't know. You can use your favorite method. And actually, together with you, Joe, and Maria Montanucci, we did partial classifications in a slightly more general setting for this capital U. But what I would like to tell you again is that this approach can be useful if you want to use your favorite machinery from algebraic geometry. Okay, just let me mention that you could use also, if you are interested in scattered polynomials in order to classify them, some link with group theory. And in particular, you can investigate the monodromy group of a certain linearized polynomial, a family of linearized polynomials, basically. I won't go into the details, but this makes life even more interesting because you have many tools from algebraic geometry, from group theory, in order to investigate such scattered objects. So let's go back to our main path. So we saw in the previous slides the case in which I was interested in just one single linearized polynomial. Was good enough for me. But you can slightly generalize this idea. So now you would like to get a maximum scattered linear set, in this case a maximum R scattered linear set in this projective space, and up to require something on your code which is not so restrictive, you can always consider that the underlying Fq vector subspace is given by this. So x to the power q to the t for some t, and then a chain of R linearized polynomials in just one variable. So the question is, how can I select F1, Fr in order to give me an example of maximum R scatter linear set or an MRD with certain parameters? Well, the question is easy to be answered in some sense, but technically it could be very, very difficult to answer to this question. So you have just to consider this equation here. So you have R plus 1 variables, you write down this matrix, you take the determinant, and then you just look at the solutions over Fq to the m of this equation, and the condition for L of u of being maximum R scattered is that all the solutions are R plus 1 tuples of over Fq to the m, such that the entries are now Fq dependent. So, okay, it's just a technical assumption, but that's enough because you can still produce examples. Because the first question is, okay, I just chose this very strange shape, but it's something worth doing. Well, are there examples of this shape here? Yeah, exactly. There are at least two families, general families, but many more other families for specific instances of the parameters. The first one is called the generalized Gabidulin, which is very similar to the one that we saw before. The second one, due again to John, and later on it was studied also by other authors, which is a modification of this. So you have still k minus 1 monomials and a binomial. And if you require something on the coefficient here, you end up with an MRD code, which can be seen as coming from this scattered linear set. Okay, so really you have instances for which this machinery works. So what if you restrict yourself to linearized polynomials for which you have just monomials? Well, in this case, you can rephrase in a more geometrical friendly way the condition we saw before. And so if you just order the monomials in increasing exponent, then you can write down this determinant here. You can also write down this other determinant where here the exponents are just q to the 0, q to the 1, q to the k, q to the r, sorry. And then the condition is the following. Write down these two determinants. Now G divides F, but you can consider this equation here, F over G. And this equation gives rise to a hypersurface in R plus 1 variables. And the condition is the following. This guy is maximum R scattered, or in other words, it corresponds to an MRD code with certain parameters, if and only if this hypersurface possesses a fine Fq to the m rational points satisfying G equal to 0. This is a very strong condition, and you can apply the same ideas that we had for curves. So you can investigate this. So you can investigate this hypersurface and try to describe absolutely reducible components inside this hypersurface, and then use the version of Hasse-Weil theorem which fits with your purposes, so the so-called Langeville theorem, and you can use whatever you want. But it's now a problem about varieties over finite fields. if you want to use this approach. And actually using this approach, we could prove, together with you, Joe, that there are no other examples apart from the Gabidulin one if you restrict yourself to the case in which the maximum of the exponents, the Q exponents of the monomials, is not that big with respect to the field Fq to the m, okay? So all the exponents of the Qs must be in arithmetical progression, apart from some small cases. So this is in my opinion, this is a very nice classification result. And as I already told you, we have to use the specific Assevel theorem for these varieties, which is called the Langeveld theorem. And we could use some inductive arguments, something very interesting in my opinion. Life is much worse in the case you want to get something in a general shape. So we could get something together with Giovanni Zini and Ferdinando Zullo, but the characterization is not so strong. And even if you require just R being equal to 2, the type of the results you get is not so nice. I mean, it's not a complete characterization. But still, we could use algebraic varieties over finite fields. Now, as we saw, we could investigate scattered linear sets having an underlying FQ subspace of this type, so one variable and one polynomial. We saw the case in which we are interested in many linearized polynomials, always in one variable. Why don't we just try to generalize this way of construct scattered linear sets and maximum scattered linear sets? So do not go into the details because it could be really complicated, but the idea is very easy. So together with Giuseppe Marino, Alessandro Neri, and Lara Vicino, we just say that, okay, why don't we search for scattered, maximum H scattered subspaces of the following form? You have a certain number of variables, x1, xr, and then you have a set of multivariate linearized polynomials, which are the parametrizations that you are searching for. So the idea now is, okay, what are good choices for these multilinearized polynomials? Okay, this definition seems a little bit ugly in the sense that you have many parameters. So is it true that it gives you something interesting? Well, the answer is yes, in the sense that we could produce examples. Here I called indecomposable stuff, in the sense that they really can be described by bivariate linearized polynomials, but they cannot be described in another way. So they are really described via a pair of multilinearized polynomials. We could generalize families in order to provide scattered, maximum scattered linear sets, and so examples of MRD codes. I do not go into the details now, but we could even generalize together with Alessandro Giannoni and again Giuseppe Marino to a larger family, which is very symmetric because now each parametrization is given by a binomial, which is somehow cyclic. So, and you have clearly some constraints on the coefficients. In this way, we could produce many examples of scattered guys, which correspond to MRD codes, which are linear over Fq to the m, okay? And this is what I meant for a powerful parametrization method, okay? Now, unfortunately, in this way, you lose a little bit the connection with algebraic varieties over finite fields. Why? Because, for instance, in the case in which you are interested in just one linearized polynomial in just one variable, then, as we saw, you end up with the investigation of a plane curve. But if you are interested in bivariate multilinearized polynomials, then for some reason you have to study the rank of this matrix, and then you end up with a curve which is a space curve. And again, the idea is, okay, this space curve should have some specific features. But as you know, plane curves are much more easier to be investigated instead of space curves. Clearly, you can try to project this curve down in a plane, but then life is not so nice again. So this is, the next one is just the final part of this talk. So I know that this is a conference in finite fields, but just I would like to tell you that it could be possible and interesting just to generalize the methods and the ideas we saw before. So first, let's just have a look on what we did so far. So we consider a field Fq, we consider a bigger field Fq to the m, and fortunately, this extension is a Galois extension. And it's a cyclical Galois extension. No? So the elements are the identity and the powers of the Frobenius. Now, if you consider this algebra here given by elements of G and coefficients in Fq to the m, you end up with this nice object, which is actually can be in one-to-one correspondence with the linearized polynomials, because you just rephrase your linearized polynomial in the following way. X goes to the identity, and each power of x to the power q to the I becomes phi q to the I, the power of the Frobenius. But now this is an element of this algebra here. And also, you can see any element f of this shape here as acting on this via this simple action. So B goes to B composed with f. Now, this function here is linear. So you can associate to it a matrix. And this matrix is precisely the Dixon matrix of the linearized polynomial you started with. So basically, via the Dixon matrix, you can encode all the informations also in this other setting. Now, this is over finite fields, but what if just move to any Galois extension? Now, K and L are just two fields. G is the Galois group, say again with precisely m elements. You can still consider this algebra here the same as we did before, and you can prove that L of G, this algebra, is also a non-commutative ring, and it is basically isomorphic to the set of K endomorphisms of L. So endomorphisms of the big field which fix pointwise this, and it's again the set of matrices size of G by size of G. So in other words, this guy really is the good translation of the set of endomorphisms. Now, why don't we consider the same setting as before? So here you have an element of this algebra here. You can consider its action over other elements of L of G, just taking the composition. And since it is a linear guy here, then you can consider its matrix with respect to a chosen order of the elements of the group. And in this case, you end up with a squared matrix. And this is called the G-Dixon matrix in the sense that it depends on the choice of the group G. Well, now we have all the ingredients in order to define a rank metric code in this setting. So basically, you just require a subspace of endomorphisms of K, which is clearly isomorphic to your algebra L of G. And here you are considering as minimum distance just the minimum among the ranks of the Dixon matrices associated to your elements, to your non-zero elements here, precisely as you did for the normal finite field setting. And again, these codes have the same type of parameters and they satisfy the same type of constraints. So again, you have a singleton-like bound. So for instance, how can I check whether a certain code in that strange definition there is MRD, so it attains these bounds? Well, stay with the case of dimension 2 over the bigger field. In this case, you have just to select two elements of L of G, say the identity and another polynomial, another function. So in this case, it's very easy to prove that your code is MRD if and only if this constraint is satisfied. So for each gamma in the big field, the Dixon matrix associated to this guy here, F minus gamma times the identity, has rank at least the size of G minus 1. This is precisely the same condition that we had before. And so using the definition of John of scattered polynomials, we say that a guy F in L of G doing this job here, we call it a scattered endomorphism. Or in other words, this code here is MRD with respect to this strange setting. Now, the translation is always the same. So some polynomial, some linearized polynomial becomes now an endomorphism via always the translation in the cyclic case. So if our group G, our Galois group G is cyclic, so basically you find again the same type of constructions as in the normal finite field setting. So life is more interesting when you consider a field extension in which the Galois group is not cyclic. In this case, for instance, you do not have monomials. I mean, monomials, a sum of elements in G given by more than two terms. You don't have monomials. I won't go into the details. So you can ask for binomials or something a little bit more involved. But again, what happens is that your approach really depends on the type of the group. So, for instance, we could prove, me, Giovanni Zini, Alessandro Neri, and Giuseppe Marino, we could prove that, for instance, for some instances of the Galois group, you can have nice behaviors. But the question is open even for very easy Galois groups. And you can even have non-abelian Galois groups. So life can be really difficult. So before just closing my talk, I would like to mention that clearly, as we saw from Maria's talk on Monday, one can always choose the function field of a maximal curve of any curve, and then one can consider the quotient with respect to the subgroup of automorphism of this curve or of the function field. So this could be a good, since it is a Galois extension now, this could be a good way in order to check whether you can construct in that setting MRD codes. Because the feeling is that in this new setting, many things depend on the choice of the group. So it could be cyclic, or it could be, I don't know, direct product of something, or it could be non-abelian. But many other conditions, many other constructions would also depend on the type of the fields that you are using. So it could be that you can really have to deal with the extension. So you can consider curves, maximal curves, and this could give you very interesting results, in my opinion. No idea about the future work because we just started now, but I think that it's something interesting. So, thank you.
Thank you very much for this very interesting talk. We have time for questions.
I told you that I cited you at least 3 times, 3 or 4 times.
Thanks, Daniele. Thanks for the very nice talk and the citations. I was just wondering about, so a lot of the curve approach can be used to show that things are not scattered, yes, or not MRD or so on. For the examples, say the known examples for families of scattered polynomials, do they correspond to anything interesting in the curve world? Of, you know, the number of points, but are they interesting for any other reason?
Yeah, okay. So, yeah, as you say, usually this approach works if you want to prove that something is not good. So, okay, it's a little bit strange. But sometimes you can even do the converse. For instance, if you remember the LP binomial, so in other words, you want to consider scattered guys of the type x to the power q to the t. I wrote it in the normalized form, and the binomial is delta x plus x to the power q to the 2t. Now, if you write down the curve in this case, clearly it must split somehow. And it splits in components which are not defined over the ground field. So they are basically empty in terms of Fq to the m rational points. So, and in other words, it's much more difficult to say that something is scattered just looking at the curve, because there you should know the complete factorization of the guy. But sometimes, and this is the case of the LP, the binomial, the factorization is very easy to get. So the theorem in that case is very easy. I mean, not that in the general setting is too complicated to prove that they are scattered, but then you can do also in this way. So sometimes the factorization is easy to be detected. Yeah, but
Thank you.
you're welcome.
Other questions? One question,
Yeah.
very interesting talk. So at the end, so if you change obvious finite field and finite field extensions to function field extensions, and the analogous codes would have infinitely many elements.
I mean, yes, but it has a finite dimension over something. So, yeah, many, yeah, as the function field, yeah, clearly.
Yeah.
So you have infinitely many code words, but yeah, I don't know about applications. Yeah,
Okay,
so
okay.
in fact, I didn't mention.
Okay. Thank you. So if there is no more question, so we thank you again.
Thank you so much.
So let me take 1 more minute from you for a very important reason. Just to remind you, yesterday we had our last poster session. We had these wonderful works presented by Thiago Verissimo, please stand, Raul Mastro, Luiz Scolari, Daniel Silva, Luana Costa, and Luiz Brittner. So I invite you in a round of applause for all this wonderful work. Okay, let's go for a coffee break.
Fazer? Trocar pilha? Ah, tá.
Sabe quando dá bug? Não deu, né?
Não. 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 Vamos tentar trocar a pilha?
Mas essa é pequena, não é? Olha, galera, é pequena, não tem pequeno aqui.
É grande. Ah, tá. Essa aqui.
Estranho.
Olá, Cícero, bom dia.
Você precisa do... Já tá na hora. É só pôr o microfone nele. É porque o pointer não funciona.
O pointer não tá funcionando. Olá, professor, bom dia. Com licença.
Eso para me sentir un astro da TV Globo, né? Isso aí, ok. Perfeito.
Professor, a gente pode guardar a gravação da apresentação?
Sim, claro.
Aqui para frente, para trás e aqui no meio é o pointer.
Para frente e para trás são estes.
É, para frente, para trás e o pointer aqui.
Tá ok. Perfeito.
Eu vou usar esse aqui mesmo, que já está ali em cima.
Boa apresentação, professor.
Obrigado. Opa.
Okay, so welcome everybody to this last session of the meeting, which will start with the talk with Professor César Polsino Mires from Universidade de São Paulo, at São Paulo. And he will speak about essential idempotency in algebra and coding theory. Thank you.
No. Good morning to everybody. Thank you very much for being here. As Cicero said earlier, I cannot be grateful to the organizing committee because I'm a member of it, but I'm grateful for your presence. And well, as was said, I will talk about essential idempotency. The essential part of the talk is the essential idempotency. You see, coding theory comes from many different directions. One option, which is being done for a certain group of people, is the following. Some of us are really interested in non-commutative algebra, ring theory, these kind of things. And some questions in coding theory motivate ideas in ring theory. Then we work in ring theory and finally apply it back to codes. So that was more or less the spirit of the talk that I'm going to give today. So the first idea are group codes. For a long time, at the beginning of the theory, people worked with the so-called cyclic codes. There are several ways of looking at cyclic codes. One of them is thinking of them as ideals in the group algebra of a cyclic group. So, actually, around the 70s, two authors independently introduced the idea of a group code, which is just the most obvious generalization. You look at ideals in a finite group algebra. Originally, they looked only at abelian groups, but nowadays we consider several families of groups. The group algebra, the behaving of a group algebra varies very much depending on where the characteristic of the field where you take coefficients divides or does not divide the order of the group. In this talk, I will always assume that the characteristic of the field of coefficients, does not divide the order of G. And that implies, by a very well-known theorem, that the algebra is semi-simple. That means that every ideal is generated by an idempotent. So in a way, from our point of view, studying group codes in this semi-simple case is the same as studying idempotent elements. There's a standard way of producing idempotents in a group algebra, which is the following. Assume that you have a subgroup H of your group G, always under this assumption, and consider this element. This element is just a linear combination of elements of the group done in a most obvious way. If you have an element in the subgroup H, the coefficient is 1 over the order of H. Otherwise, it's 0. And it's very, very easy to see that this, I'm doing, well, sorry. Okay. So it's very easy to see that the element constructed in this way is, in fact, an idempotent, and this idempotent is central, that is to say, commutes with everybody, if and only if H is a normal subgroup of G. When I first began to study codes many years ago, I thought, well, this is a standard idea. We should be able to get nice codes from these elements, because these elements H hat are very useful when you study structure of group algebras. But as we shall see in a minute, if you look at them as generating codes, they just generate repetition codes, so they're not interesting at all. But they are very useful to define a new concept, which is the following. Actually, I should say, when you're working with a semi-simple algebra, finite ordered as is our case, say let's call it A, it has a decomposition which is called the Wedderman decomposition that looks like this. It's a direct sum of ideals generated by the EIs are central idempotents, which are minimal, in the sense that they are orthogonal, but none of them can be written as a sum of two other idempotents which are orthogonal. So these are the minimal two-sided ideals of A. Any two-sided ideal is a partial sum of these. So if you have a two-sided ideal generated by an idempotent E, this E is a partial sum of these ones. So the ones that do appear there are called the constituents of the idempotent. So in our case, let's assume that we fixed a finite subgroup H, so as normal. So as I said, this is a central idempotent, so it has to be a sum of the primitive ones. Since they're all orthogonal, if one of the primitive idempotents does not appear here, when you multiply by all of these, it will be 0. So that's one possibility. The other possibility, if it is a constituent of H, even if it's repeated, what you have is that EH hat is E. Okay. And in this last case, of course, the ideal generated by E is contained in the ideal generated by H hat. So, I won't stop at the computations, but as I said before, essentially what happens is that The ideal generated by that idempotent is contained in the ideal generated by the H hat, hence gives a repetition code. We are not interested. So we want to look at the minimal ideals, minimal codes if you wish. So the ones that will be of interest are the ones, again, I don't know what happens, it's skipping a lot. So as I said, what we are interested in are the idempotents for which this product is zero for every subgroup. Because if it's not zero for some subgroup, it will give a code that is of no interest. So we'll stick to this idempotents we would call essential. They should give minimal codes of some interest, say. The first criteria, which is very easy to prove, but is very useful otherwise, is that an idempotent is essential if the map that you send G to G times E, this is the group, this is inside the group algebra, if this map is a group isomorphism. And that has an immediate consequence, which is the following. If you have an abelian group and the group algebra contains some essential idempotent, then the group has to be cyclic. Well, this is a criteria which is not very of interest for us, but anyway, this is one way of showing that if you have a cyclic group, then the group algebra does contain essential idempotents. Another way is the following. We have this result. We can prove that if you have an essential idempotent, then the ideal that it generates has a fixed dimension. Actually, they're all isomorphic. And then you can count the number of, I think, here. You can count the number of essential idempotents. So this means, this last result here means that if C is a cyclic group, for sure there are essential idempotents. So we get the following corollary. If you have an abelian group such that Fg is semisimple, then contains essential idempotents if and only if G is cyclic. Well, this is a technical idea. It's a way of establishing equivalence between codes inside a group algebra, which is the most natural one. And the first result we obtained quite some time ago is that a minimal ideal in the group algebra of a finite abelian group is combinatorially equivalent to a minimal ideal in the group algebra of a cyclic group of the same order. This is more or less out of context, but the interest of this is the following. When I started to work with this, with group codes, a well-known specialist observed to me that since the times of Berman, 50 years ago, there were nobody knew of an abelian code that would be more convenient than the cyclic code. So apparently there was no reason to generalize. One of the reasons for this is that when you work with semi-simple algebras, the most natural idea is go to minimal ideals because the others are some of those. So maybe you know, if you know the minimal ideals, you know all the ideals. But this is not really true from the point of view of group codes, because in the coding point of view, you also are interested in weights and minimal distance, and those are not algebraic properties. So, but anyway, when we were trying to prove that abelian codes could be more interesting than cyclic ones, everybody went directly to the minimals, and they are the same, essentially, which is what is written here. So actually, this theorem points to the fact that if you want to show that abelian codes can be more interesting than cyclic ones, you have to go to work with codes which are not minimal. And actually, we could find codes that prove that. Anyway, well, this is the definition of simplex code. I guess everybody knows them. The interesting thing is that we were able to prove that there is a relationship between being simple and the idempotents being essential. So the essential idempotents are of interest, at least for particular codes. And there's another result, which is this one. If you have the so-called one-weight codes, which are of interest, of course, you can prove that they are, again. It's funny, when it goes ahead, it jumps a lot. So here. One-way codes essentially come, again, from essential idempotents. So that shows that they have some kind of interesting role in coding theory. Now we go, let me go. But these two results, which I just mentioned, we were able to prove them for binary codes, binary group algebras over binary fields. But what if we work with fields of characteristic P other than 2? We couldn't prove, extend this result to that situation. So that's the reason for what's coming now. Twisted group algebras come from a very, you have seen, the definition of a twisted group algebra is a natural generalization of the group algebra, but it was not done just to generalize. The historical reason for that. When Isaiah Schur was working with projective representation theory, he had to work with central extensions, which is the following. You have a group, inside it, you have a subgroup which is central. And then the quotient field, the factor group is another G, then we say that G is an extension of gamma. In the language of exact sequences, is this, assuming that the image of n here is central. When you're going to work with that, if you take a set of representatives, every element in the group is a product of an element of the subgroup and the representative, you can work a little bit and factor out elements of the set of the group, G, and every element of the group algebra can be written as a linear combinations of elements of the extension group with coefficients not in the ring, but in a group algebra of the central subgroup. So essentially, the group algebra of gamma is very similar to the group algebra of G with coefficients in Rn. But it so happens that when you're going to multiply, you don't multiply like in the group algebra. You have, if you multiply one term of this like this, the coefficients, since this came from a central group, commute, but you have to compute this thing. This product is certainly in the class of GH bar, but differs from it by an element of n. So this is the kind of product that you have to define in that algebra. And this is the idea that was used to define a twisted group algebra. A twisted group algebra is essentially the same thing as a group algebra, except for the fact that the multiplication obeys another kind of rule. The important thing, of course, is to understand, again, to understand this map, which is called the twisting or factor set. It can be, as was mentioned in an earlier talk, it can be looked as something with cohomology, but we are doing everything just with algebra, with ring theory, classical ring theory. So there's a first example of an obvious twisting, which is this one, in a cyclic group to a pair of elements, g to the I, g to the j. You assign either 1 or lambda, depending on the size of the. And you can prove that if you choose lambda in this way, then the original twisted algebra and this one are essentially the same. Actually, if you prove it algebraically, you can see that they are exactly the same set, underlying set, same product. The only difference is the choice of the basis. Well, let me skip some things because my time is finishing. One of the interesting things here is that the twisted group algebra is isomorphic to this ring, and this ring is used to define lambda constant cyclic groups. So we can think of lambda constant cyclic as an ideal in this twisted group algebra. So there's a way there's a way to find the irreducible idempotence, and there's a way to define something equivalent, or not equivalent, but it's the natural extension of the concept of essential idempotent to the twisted group algebra. It's not exactly an extension because when the twisting is 1, the twisted group algebra coincides with the group algebra, and these idempotents do not coincide with the essential ones. So we call this projective essential. We have a criteria for existence, and skipping, what I'd like to point out is that first, Duarte, who will talk right after me, extended the first of our results. Simplex codes can be seen as ideals of the twisted group algebra generated by projective essentials. And very recently, we were able to prove that also one-weight codes can be seen as twisted essential code or a repetition of such a code. So you see, in a way, we found a concept which is of its interest of its own and has an application to coding theory in the end. So that's what I wanted to say. My time is over, I guess, yeah.
Thank you, Cesar. Thank you very much. Any questions?
Good.
Sure.
Thank you, Cesar. My question is, do you know, thanks for the lecture on group codes, and all the important, relations. My question is, are there no bounds, like in codes? You were talking about the problems on getting dimensions and going that way, minimum distance, so on. But is it possible to get, because in bound you have the bounds, like the singleton bound, the Hamilton bound, all these classical bounds relating the parameters. So can you at least say something on those? Are they results like this?
Actually, no. It's it's part of our project to go back to bounds at a certain point. But so far, we haven't worked with that.
Thank you.
The questions? If not, let's thank the speaker again. Thank you.
Posso permitir a gente gravar a sua apresentação?
Sim, sim. Não tira muito, senão não enxergo nada.
Tá confortável assim?
Mas tá bom.
Tudo bem gravado?
Uhum.
Esse é o botão?
Às vezes aperta com um pouquinho de força, ele pula muito.
Tá,
Tem que ser mais devagar.
Aqui vai pra trás, aqui vai pra
Tá, esse aqui, ó.
E ó, o laser.
Aqui.
Então, ali você pode olhar. 11h10 a gente começa. 11h30 é o fim.
Tá bom.
Então vamos começar.
Obrigado.
So, the next speaker will be André Duarte from University of São Paulo at São Carlos. So he's a professor here, and he'll speak about the twist group algebras of dihedral groups over finite fields.
Thank you, Cicero. So I want to begin with some problem in twistor group algebras, which is the problem of decomposition. So what is this problem? The problem is when you have an algebra or a ring, you want to decompose in smaller algebras or smaller rings. How can you do that? For example, in the semi-simple Artinian case, it's easy because we have a theory that deals with it. And the theory is following the theory of Wedderburn-Artin. The theory says that semi-simple Artinian ring is a direct sum of finite number of simple Artinian rings. But how can we classify simple Artinian rings? So simple Artinian rings is a theorem of Wedderburn-Artin that says that simple Artinian ring is just a matrix over a division ring. So this is a very well known, and we put this together. Actually, we know that a semi-simple Artinian ring we can decompose in two ways. The first way is to use primitive central idempotence. We can do that. We have ideals, and we can decompose the algebra. The second way we can do using the Wedderburn-Artin theorem. So we can decompose as a sum of matrices over division rings. So what is the problem here? The problem here is to find formulas for the idempotence, and in the other hand, we need to find the matrices. So what is the size of the matrix? What is the division rings? So this is a hard problem in general. So in our case, we consider finite algebra. So when we have finite algebra, and we look here, let me show you these matrices, for example. So this would be a finite algebra or finite ring. So this means that the division ring has to be finite. So we have another theorem, the theorem of Wedderburn's little theorem, that states if we have a division algebra, a finite division algebra, it has to be a finite field. So in our case, if we study algebras, semi-simple algebras, finite semi-simple algebras, we have to know the fields, the finite fields here, and the size of the matrices. So we need to compute that. Okay, in the case of group algebras, there's some papers, some people work with it. For example, some people work with characteristic 0, and some people work over finite fields and try to find these matrices, sorry, let me point, these matrices and the formulas for the idempotence. Okay, so in this talk, what do we do? We do the same thing for twistor group algebra over a dihedral group. Okay, so let me remind the definition of twistor group algebra briefly. So consider a two-cos cycle. alpha, whatever this means. But actually, you can think as a function. We take a pair of elements of the group, and the image is a non-zero element of the field. Okay, so what it is a twistor group algebra. Twistor group algebra, let me point, the F alpha G is just a vector space with basis a copy of elements of the group inside the algebra. And we have this multiplication. We define the multiplication only on the basis of the algebra. And we have this element of the field. And of course, we assume that UG commutes with the elements of the field. In this diagram is just the universal property of twistor group algebra, so we can skip that. And I have some remarks. First remark is that twistor group algebra is an F algebra. Of course, there's some restriction for this map. So this map is defined in a way that we have an associative algebra. The second remark, we have that twistor group algebra is a G-graded algebra. It's a particular case of G-graded algebra. The third remark I want to mention is important because here we have the idea of cohomology of groups. So if you are unfamiliar with this notion, so don't worry, because we just use this idea, this group, of second cohomology group of G, just to distinguish different twistor group algebra. So we have a different element of the group, we have a different algebra as twistor group algebra. So we can count how many twistor group algebra we have. Okay, and the last one is a way to know when the twistor group algebra is semi-simple. So this is the Maschke theorem. The Maschke theorem states that the characteristic of the field does not divide the order of the group, and the group is finite, then we have a semi-simple algebra. Okay, so it's a way to check. All right, so how many twistor group algebra we have in our case? So here we consider a finite field, Fq, and Dn is the de Hiter group of order 2n. And for each m is an integer number greater than 0, we define the subgroup of the units of the finite field, which is just the elements of the finite field whose order divides m, this fixed m. Okay, so now we can count how many different twistor group algebras we have. So the first thing, we compute the second cohomology group when n is odd. The first case, n is odd, and q is odd, so we have just two different twistor group algebras. So when we study, we have only two. When q is even, we just have one. So there's nothing to do. We just have group algebra. In the second case, when n is even, when we compute the second cohomology group or the de Hiter group, we have 8 elements when q is odd, and we have just one and q is even. So the only thing we have to study here is the case when q is odd, because when q is even, it's just group algebra. There's nothing to do. It's already know these results for group algebras. Okay, so I have some formulas, but I can skip that because I have explicit formula for the two cocycles. So just wanted to show the formulas out of curiosity, but we have cocycles for the cyclic case. The interesting thing that this formula for cocycle works for any cyclic group, finite and infinite cyclic group. We can use the same formula. And of course, we have formulas for the de Hiter group. When n is odd, we have this formula here. It depends on one parameter. So actually, let's show something. So consider lambda A, epsilon, and lambda B, where lambda A and epsilon is plus or minus 1. And actually, lambda B is in this set, this tau. Tau actually is the transversion of the supergroup Fq2 and Fq. Actually, we consider the units of the finite field, and we take a subgroup just taking square. So this subgroup has index 2 because Q is odd in this case, and we take the representative cosets, 1 and eta. And eta in this case, of course, is not a square. Okay, in this last parameter, lambda b, we can build all the twisting for the odd case. And of course, we can do the same thing for the even case. But this is just curiosity. And now we have some ideas from group algebra. So it's a very technical, but I just mentioned one point here, because we can use these ideas to do the general case. But actually, this is a theorem of Schroeder. It's a very old theorem in group algebras. And this theorem, actually, we can use this idea to compute, using algorithms to compute the idempotence and to compute the Werder-Berner decomposition. But I want to mention that these ideas comes from a pair of subgroups, have a pair of subgroups in the group G, and these two subgroups satisfy some conditions. And with these two, we can build everything, okay? So this is the idea. In the first steps, we need to build this idempotent, as Cesar told us in the last talk. And I want to extend this idea of H hat. So with this, we came up with the idea of a demiscible pair. What is a demiscible pair? So consider a Tukul cycle alpha. And this is just a definition. In this slide, we can consider G in a billion group, okay? So in this slide, G is a billion. So alpha is a Tukul cycle. G is an element of the group. It's alpha regular. If alpha Gx is alpha xg for all x in the centralizer of G and G. And we consider all these elements and put all together in G0, okay? With this property of being alpha regular. So now this is the definition. It's a very complicated, but sorry, I have to do it. But the definition is the following. Consider the subgroup H of G0 and the map beta, which maps elements of the subgroup in the field. In our case, would be a finite field. Okay, so H hat is a demiscible pair if when you compute the Tukul cycle only on the elements of the subgroup H, a pair of elements subgroup H has this formula. So if this is true, we can build idempotence in the same way of group algebras, but now we are twisted group algebras in this way. So this is the formula. And with this, we just consider the cyclic case because we use this in formulas for the primitive central idempotence. So the idea is the following. If we have a cyclic group, cyclic group is right here. And we have a root of the polynomial xn minus lambda, n is the order of the cyclic group. So we can build in a demiscible pair in this way, and we denote the idempotent in this way. So the idempotent depends on the generator of the cyclic group and the root of this polynomial. All right. So let me show the formulas. So I'll explain a little bit because there's a lot of formulas, sorry, here, because there's a lot of computations, but I have explicit formulas. Okay, to construct the formulas, actually we use the factorization of a polynomial. Use the factorization of a polynomial to decompose the algebra. It's a very interesting link between the two theories. So if you consider C is a non-zero element of the finite field, so this is the definition. So f of degree m, such that 0 is not a root, is called a C-reciprocal polynomial of f if it's defined this way. So this is the C-reciprocal. So it just as the classical case, but instead of 1 here, we put C. And we fix the notation. So f star would be 1 reciprocal of f, and f dact will be -1 reciprocal of f. All right. So there's a bunch of property of this. So I think everyone knows the properties. And actually, what we do now is decomposition polynomial in two different ways. So the first thing, we consider lambda can be 1 or minus 1, and we consider the polynomial xn minus lambda, but decompose this in two different ways. The first way is a classical one. We consider self-reciprocal polynomials and group the other ones, the other reducible factors, with their reciprocal. And when it's even, we do the same thing, but actually we use the idea of minus 1 reciprocal to group the factors. So the first, we consider minus 1 reciprocals here, and before that we group the minus 1 with their reciprocal, the factor with their reciprocal. Okay, we have two factorizations. So just a notation, we denote, consider f, a divisor of xn minus lambda, we denote by f hat just the division. And df we denote by the derivative. Okay, so here we have the formulas for the idempotents. I just explained a little bit the formulas, but let's consider the first case, the EI. So the idempotent depends on the reducible factor of the polynomial. And actually this pi is the reducible factor of xn minus lambda. We use this notation to pi hat. So actually this is polynomial and f is a pi. And finally we evaluate in ui, which is an element of the algebra. We just evaluate the polynomial in the algebra here. And we do the same thing for the derivative. And of course, there's the other formulas. So these formulas consider the first decomposition, and the second formula using the second decomposition. All right. So here we have a first result. So in n is odd. So we have all formulas for the central primitive idempotents, or primitive central idempotents here, and use these idempotents. So one of these are actually primitive, and the other ones we have to sum with their reciprocal idempotent. This means CSC means central simple component. So it means that the ideal generated by this idempotent is in the center of the algebra. So this is the formula, and of course we have more formulas for the n when n is even. So n is even, actually have 4 cases to consider. So let me show you just the first case. The first case, n is 0 modulo 4, and q is 1 modulo 4. So we call that we have 8 different twistor group algebras. So each algebra has these parameters. So we have these parameters. We define the twistor group algebra. And for each one, we have all the idempotents. Okay. So we call that the first case is known. The first case is group algebra. So it's known, but they have other 7 different cases. Okay. We have the same formulas for the all cases, have 4 of them. We divide in 4 cases. And finally, I want to mention the Wedderburn decomposition. Okay. The Wedderburn decomposition actually consider the same decomposition. We have 2 decompositions of the xn minus lambda. Recall that lambda is 1 or minus 1. Okay, and consider the roots of these irreducible factors. So beta I is a root of pi, and qj is a root of qj. All right, so we have the decomposition here, the formulas for the Wedderburn decomposition. So the twistor group algebra is a sum of matrices. These EI are matrices, or sum of matrices. And we know that we have, when n is odd, we have just 2 cases to consider. The first case is group algebra, is known. But the second case, there's a little difference in the commutative simple component. So it means that instead of FQ, now we have a finite field with Q square elements. So this is just the difference in the odd case. But in the even case, there's a huge difference because we have more 7 cases to consider. So we divide when n is even, we have n is 0 modulo 4 and q is 1 modulo 4. we have all the decompositions. I just want to mention the first one's group algebra. And recall that the 4 cases, last cases, actually there's no commutative same component. So the decomposition is all matrices, 2x2 matrices with coefficients in the finite field. And of course, this is a finite field. These coefficients, when take Fq and adjoin a root. So this is, of course, a finite field. And of course, we have all the formulas for all cases. And that's it. Thank you.
Thank you, Andre. Any questions or comments?
Thank you very much. It's a good presentation. How do you actually compute the second cohomology group of the dihedron? Or it's a well-known result?
Yes, this is very well known because let me just write something in the board here. There's some result. Let's say we have this. So G is a group. So G is group. Can you see here? Group, G group. So we have the derivative group. So suppose that A is a abelian group. So it's the coefficient that we're using in the cohomology. We have the second cohomology, A. And here we have the Schur multiplier, which is just the second cohomology with coefficients in the complex numbers. So this is an exact sequence. And for the dihedral group, this is null. The Schur multiplier is null. And here we can compute the derivative. I don't see derivative group, but something like that. Compute this. And of course, this is a direct product of these two groups. So
thank you.
This way.
My question is about the method seems to be general, right? I mean, you pick here the dihedral group, and then they give you those equations, and then of course the decomposition used, you know, of the polynomial, reciprocal, self-reciprocal polynomial, and so on. The method is general. How the dihedral here enter in the picture? I mean, if I change the group, you could still use the general approach, of course, with a lot of new computations on the all around. But I mean, the method is general.
I don't know, but I want to think that it's general, but I don't know, because the difficult here is just to compute how many different twistor group algebras we have. So in some cases, for example, if we change this, in our case, it's a unit of finite field. But if it's a unit of the rational numbers, for example, we have infinite group here. So it's a very complicated, because I want to compute in all cases. But actually, the difficult is the theory of twistor group algebras. That's just a computation of course, it's difficult to compute the idempotents, but in the Weber decomposition, but they have a lot of cases to compute, because there's a lot of algebras in this family.
Of course, your main thing is discounting, right? That,
yes.
You know. Thank you.
Any other question or comment? Okay.
Thanks very much for the talk. This could be a stupid question, but so I don't know if you know the concept of sum rank metric code, where you have a direct sum of matrix spaces, and then the weight of the code word is the sum of the ranks. So I'm just wondering if from a given element in your twisted group algebra, you can determine the rank of the corresponding element in this direct sum of matrix spaces, and whether you could construct some good codes in that way or so.
Very good question. Actually, I've been thinking about this because in the last week, so I saw a mini course in an event talking about rank metric codes. So because of that, I've been thinking about how can you do the same thing? Because we have matrices here. So we have the metric rank. So how can you do that? But I don't know yet, but it's a very good question. Thank you.
Thank you.
Yeah, any other question or comment? If not, let's thank the speaker again.
Yeah. Okay, thank you. Ah, tá. Tá. Sim, 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 sim. Obrigado.
Okay, so the last speaker of our session, and as Firu said, in a way, unfortunately, the last one, is Claudio Qureshi from Universidad de la República de Uruguay. So he'll talk about Hamiltonian paths in Johnson graphs of posets, obstructions, and structural results.
Okay, thank you. Hello, everyone. First, I would like to thank the organizer for the opportunity of giving this talk and congratulate them for this nice conference, an excellent organization, and all of you for coming. Well, this is a joint work with Lucia Moura from University of Ottawa and Daniel Plenary and Mackenzie Power from Carleton University. Since we've seen a lot of final fields during this week, in this talk, I'll say nothing or almost nothing about final fields. But in our work, we don't use final fields, but there is some relation with a special class of code defined over final fields. And I will talk a little bit about that in the next slide. Well, let's start with some motivation. There is an important class of codes in coding theory, which are the constant weight code, in which every code word have the same weight regarding the Hamming weight, right? When we take two code words with the same weight, the Hamming distance between them is even. So it is common to normalize it. And we can define the Johnson metric, which is a half of the Hamming distance. Okay. An important open problem in coding theory is determining the perfect codes in the Johnson metric. An important tool to be used to approach the problem is considering the Johnson graph. Okay? The Johnson graph has vertices bit string of length n, which having weight exactly k. Okay, this is the weight of the word. And we connect two of them if the Johnson distance is 1. Okay? This is the same that the Hamming distance is 2. If we are working over alphabet F2, which define a field with 2 elements, there is another way to see the Johnson graph. You can take a given set with n elements, and we consider all the subset of size k inside, and you connect two of them if the symmetric difference is 2. Understanding the structure of this graph brings important information about codes in the Johnson metric. For example, maximal cliques. A clique is a subset which every 2 elements are connected. In this graph correspond to maximal anticodes of diameter 1 in this case. Okay, and we can apply the code and anticode bounds. The code anticode bounds is states that if you have a code with distance d and you have an anticode with diameter d minus 1, the product of them is bounded by the size of the whole space. It is important. This is an important technique if you want to estimate the largest size of a code with a given distance. Okay, you take the anticode as bigger as possible, and you have a good estimation for the size of a code with distance d. Another motivation is the so-called combinatorial gray code. A gray code is not a code in the usual sense when you add redundancy and you want to decode later. Okay, but it was introduced in the 1950s by Frank Gray to approach a problem it has some engineering application. Okay, for example, when you want to move from one natural number to the other, if you consider the binary expression, for example, when you move from 5 to 6, 5 is 1, 0, 1, and 6 is 1, 1, 0 in binary. You have two changes. Okay, the changes in the bits are represented with a switch, electrical switch, and the switches are not ideal. It is unlikely that they can move at the same time. It can produce error. And the solution of Gray was to take a different binary system in which when you move 1, you change only 1 bit. And it corresponds to a Hamilton path in the Johnson graph. A Hamilton path is a path which go for pass for every vertex exactly once. Okay, it can be generalized for combinatorial gray code in which you want to list in a class of objects in such a way that 2 consecutive objects differ by a small change. When you have a metric here, small change means the minimum distance possible between the elements. And it is used currently to speed up some listing algorithms, for example. And another motivation is the Pruese-Raski conjecture for finite fields. I will talk about that later. Okay. Well, let's start with some definition. I found some mistakes, some typos here. A poset is a reflexive, antisymmetric, and transitive relation. An ideal or a lower set is a subset of the poset in which if x is less than I, and I belong to the ideal I, this is a typo, the x belongs to the ideal. Okay, it is called also lower sets because when you have a lot of points in the ideal, you have all the below them. We extend the definition of Johnson graph for poset in this way. If we consider a poset in this defining this element, the vertices set of the Johnson graph are the k ideals. K ideals means ideals of size k. And you connect two ideals if the if the size of the symmetric difference is 2. If you see the subset like a bit string, it is exactly that the Hamming metric is equal to 2. Okay? When P is an anti-change, we obtain the classical Johnson graph. Okay? And study the existence of Hamiltonian path in this graph leads to great codes for KAD. Okay? This is an important conjecture of Retz and Rusky of 1993. For every finite poset P and K less or equal to n, less than n, the graph is contain a Hamiltonian path. Okay? It was proved true for some special classes of posets. And a recent countersample was found in this paper of this survey of Knudsen. And the countersample is very small, right? It's a ground poset with 6 elements. The ground poset with 6 elements. It has 3 maximal elements, 3 minimal elements, 1 through 5, 2, 4, 6, and every even element is connected with the previous element and the next one. Okay? In this case, 6 plus 1 is 7, but we take modulo 6, 1. Okay, this is the ground poset. And Knudsen, in the paper, proposed the following problem. For which poset P, the graph is Hamiltonian. There are 2 ways to study the problem: establishing necessary sufficient condition, or study the problem for restricting to a special family of posets. Right? We follow this approach, study for the problem for a special family of posets. Well, one question is if this is the only, if there are more counterexamples, okay? Or this is or the ground poset is just an exceptional counterexample. Well, we study this example and we generalize it. The ground poset can be defined for every even number of nodes in this way. This is a ground poset with 6 elements, the ground poset with 8 elements. Thank you very much. Are the odd elements, and the even element are the maximal one, and we use the same rule to determine the order, okay? And we can generalize this to define the ground poset in general. And we see, this is a main observation. If we consider the ground poset, it is almost a bipartite graph because you need to add only 3 edges and you obtain the bipartite graph, and it has another property. If we consider the ideals of size 3 in this poset, there are only 1 ideal with minimal elements, 1, 3, and 5. And the others ideals are 1, 2, 3, because if an idea contains 2, have to contain also 1 and 3, 4, 3, 5, 6, 1, 5. And this is the relation. This is a special type of graph. This is a star graph. Okay, a star graph is a graph in which you have a central node and you have the nodes connecting with all the other elements. It is a special type of tree. And we extend the countersample in this way. We consider the even elements, the odd elements, and we connect every even element with an odd element, except for one case, when x plus 3 is different to y. If we see the ground poset, 1 is not connected with 4, 3 is not connected with 6, and 5 is not connected with 5 plus 3 modulo C62. Okay? We can also take another rule here, and this is the same, but this is a generalization of the ground posets. And we can prove, it is not difficult to prove, that this Johnson graph is a star graph. It does contain a Hamilton path for n greater or equal to 3. The question is the following now. Is the ground poset the only countersample among the family? If we restrict to the family of ground poset, the ground poset with 6 elements is the only countersample? The answer is yes. We proved that I'll show you in the next slides. And the strategy consists on derive some new structural property of the Johnson graph. Well, let's see the structural results. The main observation is the following. The Johnson graph has a natural structure, a weighted graph. We can weight the edges by the intersection, okay, between them. And we take advantage of this extra structure of the graph. We define this concept. For a family of subsets, we said that a path, sorry, here another typo, this is the interval with n elements, is F full if there is an injective function from F to the edges of the path, so that F is contained in the intersection of the vertices of the edge. Okay. The intuition is we define T full. It is F full for F, the family of all T subsets of the intuition is the following. T full path is a path in which every T subset appears in the intersection of two consecutive K-sets, two consecutive vertices. And this structure helps to construct Hamilton path in more general Johnson graph. This is an example. We have the Johnson graph with 5 elements. This is a representation of the set 1, 2, 4. Okay? This is a Hamiltonian cycle in this graph. And we can see that the intersection of 1, 3, 4 with 3, 4, 5 is 3, 4. And if you see all the edges, every 2 subset of the number from 1 to 5 appears. Okay? So in this case, this cycle is 2 full. This is the main result about the structure of this graph. The Johnson graph admits a T-full Hamiltonian cycle if only if K plus T is less or equal to T. A very simple condition to guarantee that the Johnson graph contains a T-full Hamiltonian cycle. If this inequality is strict, there are some edges that is not used in the definition of T-full. So if we delete this edge, you obtain another path which is also T-full, and we obtain this condition, which is very important to our construction. If the condition holds, there is a T-full Hamiltonian path between any pair of vertices of length 2. There is, in one direction, is very easy to prove, and in the other direction, we use a very important result, the Mutze hypercube lemma, which is the main tool used by Mutze to tackle the middle level conjecture. Now it is a theorem. Well, I don't know if I will skip this presentation, but this is the hypercube lemma. The hypercube is a binary string of length n, and you connect two if they are distant ones. The distance is the size of the symmetric difference. And we can obtain, for every k, a cycle between these two levels and a set of disjoint paths. And we use it to prove our results, our main results. Very quickly. We prove then that this is the only counterexample. And let me see. We have a canonical decomposition. Every idea can be written in this way, and then the disjoint union of these two ideas. The maximal, this is denote the maximal elements, and the others odd elements. We use this decomposition, and we study. We start with the idea is the following. We start with a cycle which contains the ideas which have only odd number, and we extend this cycle iteratively in a smart way, increasing the ideas whose maximal elements are specified, are given. In this way, we proceed in this way. I will omit the details. And finally, we repeat the process and we reach a Hamiltonian cycle in the Johnson graph associated with the crown poset. Well, there are some conclusions. We show a family of posets for which the Johnson graph is not Hamiltonian. We introduce T-full Hamiltonian cycles as a structural tool to approach these kind of problems. We applied our theorem to prove that, to characterize when the Johnson graph associated with crown posets are Hamiltonian. And there are other directions to explore. For example, study other family of posets. I forgot to mention I think that two classes of poset, which is interesting to study, is the NRT posets and hierarchical posets. I think that it will be interesting problem to study that. Study connection with constant weight code over other final fields, not just with two elements, with k element. One of the things can be generalized for other. Perhaps we can take advantage of the structure to prove new things. I don't know. I investigate the complexity of generating such cycle efficiently. It is an algorithmic question. Okay? Well, that is all. Thank you.
Okay, thank you, Claudio. So, any questions or comments? Okay, so, okay, sorry.
Thanks, Claudio. I'm a co-author of this paper, and until a few weeks ago, we had two open cases, which was k equal n-1 and k equal n. So you solved?
I think the case in...
We're going to talk at the lunchtime, I think, probably about the solution.
I-1, I think that yes, and n, I am almost sure, but I had to check some details.
Okay.
It is almost done, but not completely.
Okay.
Yeah.
Okay, great.
If more co-authors have questions. Okay, so if not, let's thank the speaker again. A last announcement. I would ask you to please stay here for a few minutes because I think people from the other session will come so we can take a picture of the remaining people in FQ16.
Yeah, they're coming.